chicken. Is that the only person that likes Saturday? No way. You have to hold back now. Yeah, cool stuff. Oh, you saw me. They told me that the SAS kids were here, but they were here probably after when you were not here.
Yeah, I had to leave at like 10:30, so if they were there, then I saw like one person.
Must to be born in a hunger to buy. Hear the wish of the oppressed, to unleash get to be oppressed in style. Freedom is slavery. Your content soul. Your liquid soul. So profitable.
You're with the other place. What was his name? Sean. Pearson. What's your major? What are you trying to do?
Mechanical engineering.
Cool stuff. Yeah, we got a lot of stuff in the couple of so we're looking at So, what's your experience? What have you like, done anything in robotics, anything programming, anything like that?
That's what I'm trying to get into. I'm working on a project now. I'm building a roller coaster here in UC.
A roller coaster? Easy or you're gonna ride it? What the? Where's that? Let me see.
I'm making it now. I'm starting to use it.
How big are you talking about?
25 feet tall, and like 600 feet long, probably. A little bit less.
And where are you getting funding for this?
Science department, math department.
But they're gonna fund it?
Huh?
They're gonna give you the money to make it? How far along are you in the process? Like, who are you talking to about this?
Chairperson for the science department.
They're in?
Yeah.
Okay, that's good.
Talked to the president, and he said it sounds like an awesome idea. I'm talking to the
I've been
math
using
department
Grammarly for
now.
years. Now the great thing is Grammarly is free and
It's going
easy
pretty
to
good.
use. It not only helps you check.
Okay,
your
that
also
is
ensures
actually super exciting. Okay, well, wow. Okay, well, I just came from the summit, a bunch of like big wigs and whatever over there. They just approved I think like $200,000 for the robotics lab. They're gonna give us a bunch of shit. There's a lot of stuff. So wow. So I mean, maybe they might actually have. Well, okay. So what do you know about like the building of this thing? Like, tell me about it. I wanna.
Well, I've been I've been speaking to a couple of different like professionals who built like a bunch of these guys, and they're all getting like information basically. I'm trying to get in contact now with Mr. Knights for the architecture. I also just reached out today to the architecture professor here, Vasquez, Mr. Vasquez.
Okay, well,
We're in the
cool.
starting phase, but so far everything's really good.
I like that. That's actually crazy. Okay, that's cool. Good to know.
So is it first year or second year?
First year.
What class are you taking? This one's a
Like mine?
My presentation is like a little bit of physics, a little bit of
Learn on the job, I guess.
my goal is to teach people that don't know at least the concepts. So hopefully you like
That would be perfect because I'm reading a book now, and you need to know like the elementary level of physics, you know, like the basic level of physics, and how to take it in physics.
Let me actually show you some. Hope it doesn't take up too much time. I'm actually working on a physics engine to teach kids physics. Come on, let me see. If you need help talking tonight, I can help you talking tonight. I know that guy.
He's
a hard guy to get a hold of.
him, but we haven't been.
It says you don't get to him like that. You gotta catch him. You gotta catch him. There you go. Actually, I don't even know if I left it here. Let me see real quick. I'm looking to. Oh, there you go. Look. So I made this thing. I used to teach my. I teach at middle school too. So look, here's a little game. You know, you got your guy. The guy has drag too. Like, let me show you. So there's no much drag on the walking right now because that's the normal way. But if let me show you, if I increase the.
Star Wars
If I decrease the drag.
is now streaming, and upgrade to the Disney bundle for even more.
I made the whole thing myself. So it's a good way to get into this type of stuff. Let me put it to a number very close to 1. Look at this.
Whoa. This is the top of the line Omen 16 laptop. Powered by Intel, I
So,
can
yeah,
finally
it's
game
like you're
without
sliding.
lag, render videos, and bring this wherever
Yeah.
I go. I can stream constantly knowing it'll stay cool.
It's normally
I
set
can do
also
it.
to there's collision, so like you can push things. You know, you apply force and everything. It's all done here. I'm still working on it. It's still a work in progress. It's gonna be like a full thing, but I wanted
Watch League of
to be
Legends
basically a
videos
way to
ad-free and learn to
just-
win uninterrupted.
Yeah.
Try YouTube Premium on
push the guy. Collision detection. All people want to get into game development and things like that. Help out with that. Oh yeah, I think do I have projectiles on this? Oh, this is not the updated version. I might have the updated version. Hold on a second. Because I got projectiles too. But okay, are you set? Am I taking your time? No, do it. No, it's your time. Okay,
My
do it.
time to shine?
Yes,
Send
yes,
the
yes.
presentation on your email.
Okay, cool. I was waiting for that. Okay, where is it? Go ahead. Can I just go? It's showing up. There you go. And I guess press the
Oh
space.
yeah, okay, here. You can take a seat. I will be in charge of the entire
Yeah. Do it.
goofy area.
It's a cool thing. Okay, so. Well, yeah, you know what to do.
I stole it from
the sample template things. Okay.
What the?
They move back.
Flimsy, what the? Scared the shit out of me.
So I'm developing a course on introductory control theory, and control theory is this sort of branch of mathematics that is very complicated, and it has a bunch of different prerequisites, things like differential equations and different ways of representing functions and how they change, which might be a little bit inaccessible to somebody who's never taken a calculus class before. So today I wanted to talk about one of the most common sort of beginner control theory problems, that being the inverted pendulum. So today I'm going to give a quick overview of the physics of the pendulum, a basic idea of the methods used in order to balance the pendulum, and then I want to get some like feedback. I don't necessarily know like everyone's skill level and understanding, so take as much time, ask as many questions as you can. I want to make sure everybody has like a very good conceptual understanding of the concepts. So here we go. We got a discussion of control theory. We're going to talk about the concepts for the pendulum. We're going to apply this to a model, and then we're going to go over the model, dissect it, and talk about applications, and then we'll go from there. Well, look, I already said this. So yeah, I'm going to be glossing over a lot of physics and a lot of different things just so that you can kind of understand what's happening. But the general concept should be pretty simple because it's things that you would be able to observe and test in real life. We're going to be talking about equilibrium, which is a special state where things have no net force and no net torque so that they can basically just stand still, right? That box, me, these things are just in equilibrium because they aren't moving and they're just doing nothing, right? So let's begin. Control theory. Control theory is the study and design of dynamic systems. And with this, it gives us the tools in order to build and simulate models, predict interactions between complex systems, filter and reject noise, and select the proper hardware. So what's really important is that with a deep understanding of how signals interact, we can know what exact sensors, what exact bits and pieces of technology we need in order to build our projects, right? Like, let's say you're building your roller coaster, you need to know exactly like how the, let's say, magnetic braking mechanism works on it, and you need to know exactly what sensors, what type of values you're going to need, for an example. So today's problem is the idea of the inverted pendulum, where we are going to take this system, which is made of two servo motors, one inside the box and one up here. Servo motors are special because, like a normal motor, which you apply voltage to and it spins, a servo has what's called a rotary encoder, which makes it so that you can tell the angle of rotation out of it. So that's why there's this little indicator for the angle, so that you know exactly how far it is moving. This is important just because if you don't know that, then you don't have any understanding of the system while it changes, if you have fluctuations in voltage, or if you miss some sort of like hidden resistance, then your model gets all screwed up. Yes?
What do you mean by filter and reduce noise in the last line?
Okay, so, can we go back? Okay. Signals ideally shouldn't have noise, but they do, right? So things like gyroscopes, which is one of the most common noisy sensors, they fluctuate a lot. Things that you wouldn't necessarily consider, things like gravitational fields, maybe like air currents, if it's like some sort of air sensitive sensor, a magnetic field, maybe you have some sort of magnetic inductance that's acting upon your piece of hardware that you don't notice. If you can understand that these forces are happening, and you have a sort of idea of the desired outcome, then you can realize, hey, this is wrong, it should be more like this, and then you can filter it out and make it more and more accurate. You're basically making it so that your mathematical models suit the real world where things tend to not go exactly as planned, right? So, is that it?
Yeah.
Wonderful. So today we're going to see how to make this thing oppose gravity, right? Equilibrium. This is a concept in physics where things stand still, right? And that's basically it. This is a very simple concept, I would say, but like it has a lot of complicated applications. So usually when you think of something in equilibrium, it's standing there, it's doing nothing. If you push it, it begins to do stuff, right? You apply a force, you apply a velocity, it might begin to roll, it might begin to fall over. This trapeze guy right here, he's holding on to dear life with a little stick, right? And this is important because what he's doing here while he's walking on his little trapeze is that he has a very, he has a lot of control over his center of mass, which is the most important thing about equilibrium. If you understand exactly where something is centered, then you can balance it upon that center, and that allows you to make something that, like you can support the same dude from different spots, but he's walking on a tightrope with his balance perfectly set up. And the reason that you want to be right at the center of balance is because when you hold the stick, right, you're applying a force onto that stick and you're holding it upward, and that's causing it to stay in space. So the net force on that object is 0. But if we look at this rod, it's actually kind of bent around because at the edges, there is also forces, but they're being upheld by the stick itself. But because they are out on like a rotary arm, they create what's called a torque. And torques are like forces that rotate. And at the center of mass, when you hold your object at the center of mass, these torques cancel out because there's a clockwise and a counterclockwise one, and they will they cancel out, right? If you've ever been on like if you ever like bounce a pencil on your finger, you realize, hey, if you move it too far to the left, it falls over. Not because the net force is not 0, but because the torques are acting upon it in a way where it'll fall over. Do you have any questions on this, or?
No.
So with the car, the 2 wheels, right?
Mm-hmm.
And I guess I just didn't know the name of it. The wheel that says forward, that's the torque. Is that it? Because when the wheel says you push the car on this side and this side, right? The wheel, the arrow is on the. I'm explaining this so bad.
So you're saying like the wheel applies a torque onto the ground?
No. They apply torque to each other. So like you have a power this side, power on this side, right?
Mm-hmm.
They're connected, right? So when you apply more power on this side, then it starts to move this way. You apply more power on that side, but that would be like torque because it's applying torque to the middle, right?
Conceptually, yes, but in practice, it's a little bit more complicated than that. Cars have what's called a differential drive, which is a special type of gear that gives different output velocities for the different wheels, which is why you're able to turn and why, even though you're on a fixed axis where you're rotating around a set point, the inner wheel doesn't rotate faster than the outer wheel. But for the idea of you give power to this side, it moves this way, and if you give power to that side, it moves that way, then yeah, these are torques that are being applied. And then when you put them together, there's no net torque because both of these wheels are acting
And then it goes
in
straight.
the same direction, correct. So that's basically the fundamentals of equilibrium. Hello, nice to meet you. Do
Nice to meet
you
you.
by any chance understand what equilibrium is, or do I have to go through the whole thing again?
He was here. That you gotta keep going. Just catch up. You'll catch up.
Basically,
You're my guy.
things will balance. Hold the pencil on your finger. If you put it at the center of mass, then it doesn't fall over because there are no
So airplanes.
forces. Yeah, like an airplane. Let's go with that. Center of mass, that's important, right? And if you're thinking about it, right, this little pendulum here has 2 states where the center of mass is being balanced. When it's fully downward, and let me see, stop being this thing. When it's fully downward, it's around its center of mass because the mass center is this like parallel line. And when it's up like this, it's also around its center of mass. But the thing is that when I let go, it falls over. And the reason for this is because there are 2 types, or I guess 3 types of states of equilibrium, where there are stable and unstable equilibriums. So down here, no matter what I do, if I push it over, right, it's just going to go back to where it was. But if I'm up here, even though for like a moment, the net force and torque on this object are 0, any small fluctuations, any like when I let go, I'm going to apply a force onto it, right? It is going to fall over, and this thing swivels. So this is what we would call unstable equilibrium, where the system moves away from its initial position, and it goes back down to this much more stable system. And this is kind of a problem, because if you want to balance this thing all the way up, then if it falls down every time, we're at a little bit of an impasse. So let's go plug this thing back in. Now, what do you guys think is a way of maybe getting around this unstable equilibrium system? Do you have any ideas?
Change the center of mass.
Change the place.
Those are both good suggestions, where if we keep moving the center of mass, right, maybe we can counteract these torques that are being applied onto the object. So these are very wonderful suggestions.
Tape it.
Keeping balance. So
Hold it.
taping and holding are good ones too. Unfortunately, it requires a human being to be there, which eventually the overlords will get rid of them all. So, keeping balance. Let's assume for a point, right, that we can just apply voltage to this motor and it goes up and it stays there. As we said before, it is going to fall, and there's nothing that we can do to keep it from falling. Someone will breathe too hard, someone will stomp on the floor. I don't know, maybe there's like a electrical force or something that applies something to it. It's going to fall, right? So we have this thing called a PID controller, and when I said that control theory has a lot of math and a lot of difficult concepts, this is one of them, where this is a three-part controller which takes three aspects, called the proportional gain, the integral gain, and the changing error value, which are all different multiplications and analyses of similar concepts or constants. So here with the proportional gain, I don't know if it's too small to see, but we basically just multiply our value by a constant. Here in the integral gain, we take basically an area, and these all measure either the output or the area perceived by the object. And to go more into that, it'd be a little bit too complicated. But and then the derivative gain, or the error changing gain, takes like the basically infinitesimal change in motion with time, and it sums them all up and puts it into a process. And what this does is it causes, as you said, the center of mass to basically go around and change back and forward. It wiggles very slightly every time the computer basically sends a signal that says, hey, this is what's happening, something is about to change, and it says, okay, well, I'm going to go back through this loop, and I'm going to add another value which is going to account for that change. So, yes?
Then that value is the amount of power that you give to the motor, right?
Yeah, so this would be like our, I guess like our plant or our actuator here, and then this would be some sort of signal which would be one of two voltages in this system, but if we consider a more simple one, it would just be a single voltage. So do you have any questions about this before I go on? Okay. Oh, and one more thing, control theory, we talk about this thing where everything loops back to itself, right? This is called feedback, and this is what we create a closed loop system where we can better understand how it changes with respect to itself, which is very important. Yes?
So how do you, okay, so you're trying to get to the equilibrium. This is a thing that I still don't know how to myself exactly, but so how do you find how do I explain this? You're trying to get the values correctly, right? So that you can counteract the forces that act upon the system, right? You need to find the proper values that counteract everything properly.
Yes.
Like, is there some math formula to get that? How do you do that?
So
or is just testing? Because I mean, you just
in physics, right, we can create a pretty good Newtonian model for these things. So like, those are classical mechanics, where we know the mass of this object, we know where the center of mass is, we can calculate these things, and we can find the moment of inertia. And what this will do is that it will say, hey, in a frictionless system, we could potentially apply this much voltage, and it will go up here. And I would love to do the derivation, but it's a little bit too time-consuming. But it's basically 90% of the way there. But it's going to be wrong, because this thing's going to fluctuate a lot, right? And that's where the PID controller comes in. It says, hey, I know my system is not necessarily purely accurate, but this thing will correct for any minor changes. Once I'm up here, all I have to do is wiggle around a little bit, and everything works.
So it's never actually at, well, it is for like a split second, but it's never truly at equilibrium.
Well, what's funny about this is like it's an exaggeration. Once, I mean, I think you already saw it, but assuming no spoilers, this thing will stay pretty stable in its system because every time this loop happens, right, the computer processor, this is every time a sample is taken, and because of how fast computers are, they sample at a very high time, and they create a very almost continuous looking thing, even though computers are a discrete system instead of a continuous one. Any questions here? Just make sure. Yes.
So does it learn by its mistakes from the beginning, or does it continue to do the same thing using intervals?
Well, I would say that it doesn't necessarily learn anything. If your PID controller is tuned inaccurately, it's going to break, okay? And it's just going to do bad things. If you put it along constants, have a good day.
Me too. You're gonna go over here. Do you guys meet any other days?
You should.
We sometimes meet on Tuesdays if you want to come in.
If you wanna do like other stuff, like you can contact us usually is the right way because that way we can help you. We have like robots and stuff that we can show you and stuff. We do that after this, but if you want, send me a message on the phone here.
You have a business card now?
I always have it.
Real fancy.
I just saw that he had one today.
I had this since before.
No, I had no
Thank you
idea.
guys.
Bye.
Little one.
That's since before I met anyone.
There goes all my survey results, but
It is what it is. You got me.
what were you saying? You were asking about how it learns, or?
No. Well, she was saying that I was gonna say that from what I understand, the thing is that like my experience with that is that like it's a piece of shit to test because you have to keep changing the values. But then the interesting thing is that like AI,
Yes.
like genetic algorithms, you can use it to like start predicting those things, right?
This is actually, I don't know if it's here, but I wrote about this a while ago. No, it isn't. But because
It's block post.
these are differential equations, right? And that means that they usually are the results of like multiple different variables, and we're testing them. We're actively using like a tuning software or something like that. We can actually represent things like this PID controller. We can use a neural network. We can use a transfer function. We can use all these different types of methods that are allowed for like multivariable systems. We can apply them to the PID controller, and we can use that as a way to automatically test the controller's viability. Of course, we can always just predict the values and use it in that way, but these are all just different ways of getting to the same ends. And for the very simple demonstration right now, we just assume that we have all the right constants and we have everything set up. So without that, I'm going to go to the next slide. Okay. Oh, I'm supposed to play the thing now. So I'm going to show you exactly what PID controller does in action, right? And this program is just a simple MATLAB Simulink script. If it was on the computer, I would show you. But I'll show you a block diagram that explains what's happening. And what this will do is that it will, because it knows its angles, it will begin to give the system energy. And, oh, I already did it. And it will swing into its inverted state. And even if I try to like screw with it, it will just keep going back to what it wants to do, because even though there's like these rapid changes, because of how the PID controller is set up, it will read these changes. It will read the essentially slope of like a voltage graph like this, and it will say, hey, I'm moving really fast, I need to move really fast in the other way, or I need to find a way to recuperate myself.
Oh, now I see why you use differentials. Okay.
Yes, and that is what this is. This is like one of these slopes, and you can see exactly how even over like a very small voltage, like this is between 1 and 0.4 volts, this thing changes a lot. It makes a lot of little micro adjustments, and it does all these little things in order to keep itself at a very, very balanced step. And if you want to come up, you can actually look at how like much it fidgets and all that, but I'll leave that for a little bit later.
I like this thing.
I'll let everyone be able to have a little time playing with it as well.
Check it out, guys.
So in control theory, typically these large differential equations and all these things are represented with blocks, right? And this is like the easy stuff to understand. If you have the blocks and you know how to arrange the blocks, that's pretty much good enough for now. Or it will be good enough for like any sort of intermediate, beginner sort of understanding of control theory. You don't necessarily need to know how to solve all these little things within their own special domain or whatever. But we're given a reference input, and this is the comparator, which is like the source of the feedback, which is a part of the closed loop design. We have a controller. In this case, we have a PID. The actuator, which would be the motor itself, and then a process, which is just like the output, right? So you have some voltage, it outputs, and then it will read its angles, and it will. This is the sensor. It reads its angles. It feeds it right back into that. The controller realizes, hey, the angle's changing too fast. Hey, the angle isn't changing, or it is, and then it will say, hey, keep adding, over and over and over again, in a very recursive manner, very simple, similar to how recursion works in programming. Any questions? Okay. So, in summary, we can use models to simulate difficult issues in complex systems. By using feedback, we can account for slight adjustments in the system, things that we wouldn't necessarily recognize, and like friction or air or some other external forces that we don't necessarily want to model around. The pendulum is just one application of this theory. I think that learning control theory helps out a lot because it lets you identify systems, understand exactly what actuators or plants are being used, maybe understand exactly like these little changes within different like systems and how they build into something much greater. You know, the one little piece and the two little pieces, and you make a whole city or something. I don't know. So having an intuition for these things is how we can do complex tasks, and it makes it easier to design, program, engineer, and build all these things. So I think control theory, everything kind of leads back into it eventually, even if you don't necessarily have to be the one person that's solving all the differential equations or whatever. So do you have a question or?
What is C?
C?
I know it's controller, but like what is the mathematics?
CFS is just, well,
Is that just speed? No, what is it?
CFS in this equation would probably be the PID controller, which I guess this is on the S domain, so it's it probably takes in a transfer function, blah, blah, blah. All that we need to know is that it represents a function that is probably the PID controller, so C in this case is representing these three different values
that's
added
the
together.
three.
Yes.
That one, just C.
It's an abstraction.
That would be the controller. Obviously, this is a little bit inaccurate because we don't actually have a process here. It's just the actuator, and then that's the output. So this is a little bit more accurate. Where
So it starts by gathering the data from radius 0. So once it's like in the middle-ish, like when it's weighing, it's like seeing that it's like more to the positive or the negative side.
yeah,
And then E, and then like.
then adds or subtracts if it's too big or small.
Intervals, and then 4s, and then
And that is the general basis for the control theory, the control law of the system. So I had a QR code. This is going to be like I was going to use this data points for a presentation tomorrow, so that I can show off like, hey, this is a class, how much I understood about these concepts. What's up? And I guess you could do it.
Yes.
You get all four of you will be very important bits of data.
Exactly.
Okay, wait, Fernando. So you're taking physics right now, right?
No.
No? Do you want me? I'll explain this to you in a little bit. So if you want to hold on to that survey, I can like teach you it in the background.
Bet.
And that ends my presentation for the day. Let me know if you have any questions, because I will talk about this for maybe like 10 more minutes, and then I'm out of energy, right? So. So funny.
Oh, Karames is in the chat.
He's in the Discord chat?
No, he's on YouTube, I think.
YouTube? What's his name?
Hold on, no, he hasn't. Let me tell him how to type on YouTube chat. Hey, Professor, how you doing? Actually, no, you just tell them. Okay, you're on YouTube, right? Can you open a YouTube tab and show how to do that?
I can upload the entire stream on. Oh, that's gonna look really bad.
Yeah, you should show them.
How do I view? Oh, there you go. I'm a genius.
Yeah, but
Not seeing anything.
What do you mean? Oh,
Just
well,
like those.
yeah, but like, what if like Felipe has like some weird anime stuff on his YouTube?
I
So-
introduced. I have nothing in there.
What if the pendulum had more mass? How
Then,
would that affect the equation?
well, with what this model
I
does,
have
right?
to add more to the power, right?
So-
What proportional?
Yeah, the power is proportional, right? So here, this one considers the kinetic energy of the system, part of the planet. And so if you create a more massive pendulum, or even a pendulum with like an optic center about mass, like you put like a weird shape right here or something, it will eventually figure out something, assuming that you have proper enough variables that it can get up to a state almost similar to the output, then it will try to balance itself out. But like here, what I can do is I can drop down the energy, like the mechanical energy, and it will have a hard time figuring
This
out how
is
to get
live?
up.
I have no idea.
Yeah.
What?
Yeah.
I told you it's live.
You never knew? All the
No, I didn't
presentations
know
are
this
live.
one was live.
Okay, 1 second. So, just let me so the professor can do his thing.
So if I drop this down, then it's gonna be like, it might figure itself out, but it probably won't. We'll see what happens.
Can I?
Okay.
Hold on, let me check what.
Infinity, right?
Does he have a YouTube account? Or does
What?
he know how to like use that?
He probably does. Probably has his school one. I'm guessing. Okay, so he's on YouTube. So professor, if you see, you would have like a chat box. If you're on the computer, you just type something here. You do it. If you're on your phone, let me check. You can do it on your phone too. 1 second. Oh yeah, in the stream at the bottom. Basically, can I get closer to the camera? Let's see. Let's see. Oh, how long is it? Yeah, I'm waiting for my.
Wait, this is
I feel so dumb.
What's really cool?
There you go. No, that's so bad. If you see down there, you just type down there. Oh my god, yeah. There you go. At the bottom there, you just type. Look. Like that. There you go. There, you just type. Type
Girl,
the
no
message
one's.
there.
Oh, there it is. There we see it now.
Yeah.
Yeah,
Yeah. And when you type, it will show up here on our screen. Okay.
Here. I feel like my phone is.
Oh, but by the way, like even though
Look, my phone is better. Definitely.
Yeah.
is it better? Is it like like an OLED or something, or
Yeah, low brightness, I think.
low brightness energy?
Bro,
I liked your presentation.
Thank you.
It was very clear.
I'm sure it was very clear.
I think if you want to improve it, you should just like I don't know, like make one side where the graph is just wording, and on the bottom is the mathematical part. You know what I mean?
Yeah, I was
Because you had two of them. There was one that was just like the wording, and then you had the other one that was just the math. But I feel like you should just put them together. They can see it all at one. You know?
Yeah, that was one of those things where I was like, do I want to make this like look good, or do I want to like dump a bunch of words on something?
No,
or-
but you did really well to like
No,
make the
no,
meat
no.
stick. You know what I mean? Like stay where like the actual thing is. You know?
Yay!
The actual thing. So it's good. And it was really like I like it when it's clear and it's like not long. That wasn't long and clear.
Thank you.
I enjoy how simple it was.
Oh, wonderful. There's because this is like a part of building towards a course next semester. Would you be interested in taking a class like this? I wouldn't be teaching it, but someone else would.
Yeah, sure.
You probably will be teaching. Then we'll make you teach. But what?
I've been taking control theory like basics, so I'm just like.
Sorry. So that I want to tell you is that you might wanna. I'm not sure. Depends. I found it very interesting when try to understand what PID really is, but like each one and how to describe them, right? So like proportional is that like you made a mistake by this much, so you correct by that much, right? Then you say that.
Basically, because it's a little bit more difficult to explain, you need like a graph of like some sort of area or something. But it talks a lot about taking like, remember how we were doing that filter and how we took the integral of it using like small infinitesimal values added together? That would be like part of like the total voltage relating to change, and then there's like a constant. It's
But
it's
that's
tough,
but that's what I'm
yeah.
saying. Like something like that, I think would be, like being able to like you to put that there. Like the proportional part, I think is the easier one. I'm dumb. I understand that one kind of like mistake. But this much you like make it. The arm is falling by this much. You correct it by that much, right? And then the integral part. Like I remember you showed me that thing with the curve with the curve. Wait, did he just type? Oh no, that's. I thought that was him. The curve with each of those like.
The voltage spikes. Yeah.
Yeah.
Well, it was a voltage spike, and then it had like all of the what should I call it? All of the some values.
Like this?
No. It was something
Just
like.
pick one of them, and we'll just look at it.
Let's see. Let me see. Look for it.
Oh, by the way, PID controllers is also useful in what is it called? Your driving things, but
Oh, you mean
that's what you do for like the path findings that you have for the PID controller.
No, yeah.
But you can
no.
also use machine learning algorithms to teach it, so it might be better that way because.
Well, no, but that even the machine learning uses PID, but like no, it uses
Yeah, but
PID
like you can use the machine learning to tune the PID.
to tune the PID. That's if you guys, it's super interesting that people say that like the Teslas get faster over time and things like that. That is true. It's because they use AI to tune the PID to even better.
Oh,
That's why, like they
But
like.
I thought they made the battery. Or
How do you download the battery?
no, the download battery.
No, but that's it. With a download, they made the car faster. It's because of that. It's because like they changed the tuning on the PID and it actually made it like better with AI. AI was able to find a better PID solution than any human could.
Oh, that's how they thought they used the AI to find.
Yeah,
solutions.
and they
Yeah.
could only do that because of all the data that they had from the cars, basically.
Mm.
So wait, hold on. So integral. Let's see. This thing, like this thing right here. This guy.
Yeah.
Because you sum all those guys and that gives you the actual value, right?
Well, I mean, you can
But
express-
actually,
like,
it
we're
says
sitting
it says
here,
right there, right?
it's expressing the integral as this is like a calculus 2 concept where you can express an integral as a summation of areas, right? Similar to like our controller. But what's happening in the actual PID controller, the loop that you're looking at, is that it's summing the three values from the different controllers.
And
from
using that
different
as the
methods.
actual value, right?
So this is basically what the computer's actually doing. It's taking a sum of the areas as part of its as part of the integral gain, and it's adding that to what would be a slope that is changing on this thing, which is also correlated to a constant, which is like the notion of the of some function of either the angle or the voltage.
Thank you.
Have a good one.
You too. Have a nice day.
But yeah, showing this stuff, I want to see this graph because this graph actually helped me out a lot when I was looking at it. I think this graph made me understand it better.
Yeah,
Because
also
you
get
have a-
scared about,
And the other
calculus,
one, sorry,
like,
the
being harder, but
the other one that you showed me this other graph, the graph for.
trapezoidal approximation. Is that
I think, that's one that's trapezoidal approximation. That's one, but then there's the other one, the other cool one. That one's an interesting
Oh,
one.
you're talking about the normal distribution?
No, the one that made it so like the reason that you need to go double the speed when you're
The
analyzing.
Nyquist rate.
What is it called?
Nyquist. NYQIST.
NY Q
Q, yeah.
NyQuil
Like IST. QIST.
QIST. Like
Nyquist, look for like
frequency.
Nyquist rate or
What
frequency
frequency?
or whatever. The idea is that on this.
Yeah, this thing I thought this was super interesting to understand this part. But where do they have it? The one where they show all of the thingies. And there's actually like an algorithm to like optimize for this shit. Like,
Well, not
The-
really. The entire theory behind this is that no matter how many, you have to take twice the amount of samples of the frequency, like this frequency right here.
yeah,
If you take not as many samples, it is going to be inaccurate. It's going to either alias or it's going to just give you something that's basically wrong. But if you were to take twice the amount of samples as the frequency, as the function, then you can get a perfect recreation of that signal without losing any data.
Carmen says you are doing a great job.
Oh, thank you. That's one of those things that I also wanted to cover, or that's not the thing for this presentation, but it's something that I do cover. the Nyquist frequency. That's like really easy to understand. I'm scared about like other things, you know.
No, I don't get it.
So you don't get it?
No.
Okay.
You're talking words.
Big
Talking
word.
to the wall.
Yes.
So let me find a good picture, and this will make it easy. Allow me.
That's right.
One.
On derivative. Well, the derivative.
The derivative would be like infinitesimal slope.
Right. That is a hard one to fully understand, but I mean, if you can, what I was like, don't get too hardcore into it. If you're gonna do it, is like, just say like, okay, if you go far enough into one direction, all values kind of become like close to zero or close to zero, right?
Well, what you can say is that you just call it the slope of the line at that point, and then
Yeah,
people
but-
understand exactly what that means, even if they don't know how to calculate it. That's,
Yeah, it's a bit weird to like even say it, but yeah.
It's-
Like,
that's
I
exactly
think
what-
derivative is probably the hard, at least to me, is the hardest one to like. I kind of understand, but like, it's the hardest one to like fully grasp, I guess.
You're not gonna like differentials.
Yeah, this is fine. This is a good picture. So, oh, I can make it bigger, can't I? Open image in new tab.
That guy that you made that you showed me that video from that guy had like the perfect graph.
Yeah, I love that he did. I have
Yeah,
to find
because
the video.
because he made it one that like basically the best one is when like all of the values that you take end up being on the middle, right? Because you did it and like you get like a very bad signal because it's all the values on the middle. That I think because that shows you how wrong you can be if you don't take double speed, right?
What is this used for?
So this is how we would convert typically like an analog wave into a digital signal. Usually people will say something like, oh, well, the analog is better because it has everything. But if you were just to sample a signal at twice the rate, then you'd get a perfect recreation of that thing every time. It's kind of like, I don't know, like if you're making like a Taylor series, how you can make everything like a summation of sine waves or something. It's the same idea where like you can just recreate a perfectly done signal. All you need is a tool that can sample a signal at twice the rate. So this guy takes samples at, let's say, whatever this rate is, right? Delta x or like delta whatever. It's on some time-based domains of delta t, right? And he takes samples here, and this really cool thingamajig signal gets completely destroyed and it turns into like this sort of sinusoidal, I don't know. They're all sinusoidal, but you get the point. It's half the frequency, or half, like a fourth of it. And so what you have to do is you have to take samples here, and then that would perfectly recreate the wave, because we understand that it would turn into something that if we have like a wave that kind of looks like all sawtoothy, it will eventually we can process it as a continuous wave, something like this, right? Yeah, because nothing right here at these points, right? It's impossible to because it just completely it's no longer smooth and continuous. You can't consider a continuous function. So then they apply some like maths, and that allows you to recreate the signal at a better as a sinusoid that it actually is, right? And that's it.
Yeah. What was the thing that I was thinking?
No thoughts.
No thoughts, I don't do it.
No thoughts and comments.
Well, yeah. The thing is, you have shown me like that's why I would like you to see like show other people, because you help me out a lot, especially with.
Yeah.
For me, I like the graph. I like to see. I don't know. With me, is that like I don't care until it hurts me, kind of in a way, a lot of these things. So I didn't realize how important that was until I realized that like if you don't do it, the signal's just shit and wrong, right?
Mm-hmm.
So if you can show people that like if they don't do it, then it's you get a completely wrong result. Like you show the most extreme version of the mistake. I think that's a good thing to do. I don't know, but that's computer science is like that a lot. You always work on the most extreme version of the mistake, right? You always want to work for the worst case scenario and try to optimize that, right? So I don't know, maybe that, because I'm thinking about like obviously it's all theory, but I always think about just like the real world usage of all the things, right? And yeah, I don't know, that's my opinion on it.
Oh, engineer.
Yeah, it's a bit confusing. But the cool thing is that because like an integral is a really funny way of adding stuff, that's like the kind of the teaching methodologies. You take very small changes, right? Like just like based on the sample rate or theoretical delta x, right? And then we can make assumptions about the area, like these little trapezoids. You make assumptions about how it changes between points and stuff like that, and then you can kind of explain calculus without needing to do like a derivative or some other garbage, you know. It's all.
Show my game.
Show your game. Where's which one?
No, it's on the other thing.
The other thing.
Why don't I see?
I want to see it. Oh, it's like in the other.
Oh, wait, hold on. Let's see. Ahmed.
504 gateway time down here. This one.
You didn't see my comment. Okay, whatever.
I saw your
need
comment.
you to
Wait,
see it
did-
because this is stuff that we're gonna be teaching. What's up? Hey, how you doing? How you doing? Engineering too? You do engineering too? Nice to meet you.
hello.
So this is something I've been working on. Also, it's a working project, but it's a game. Well, it's a game more than anything, but it's fully developed by me, but it's made so to teach kids like about physics, but like in a fun way. So I'm trying to basically make like a fighting game, but with full physics on it, right? So if you see this, you punch this guy, he goes, you knock him back. All those are made with functions, and you can like by actually making the functions, you can teach the kids like how the functions works and everything like that. For example, the one that I've been playing around with lately, the one that like makes me do a little giggle is the drag function. Well, not the drag values, which if you make them closer to 0, it's like you're sliding on ice. See? And if I push that guy, he goes sliding, yeah? And with this, you can explain like all those physics concepts and things like that. I think is a cool thing. And everything is based on the things like that. There's the more hardcore stuff, especially, and this is the thing that I wanna get. Hopefully, well, I didn't get any of the people that were working algorithms with me from last time. But one of the ones that I've been really enjoying is the collision algorithm. Which, where do I have it? Right here. This guy right here. It might seem like not that much, but this for loop, I actually only got how this for loop actually is good when I put it on a graph. And this is probably has something to do with graph theory or something like that. I haven't gotten into graph theory. I guess I actually think I just stumbled upon the right solution, but I thought that was actually pretty cool for it. So I'll give a quick one on this because I'm so passionate about like just this thing. So what is a collision?
Something crashing into
Change of momentum.
Change of moment. Yeah, but yes, but okay. So good one. Whoever did that. Okay. I just saw that. It says loser on the chat. Yeah, no, good. So at least programming wise, right? You have positions, and those positions have like you have things, and those things have bodies, and those bodies have positions represented in a. Let's say we're just talking 2D, not to get too complex. It's just a Cartesian plane, right? So this thing has a specific body, and it has a radius and whatever. What in a way that how can we represent collisions is when the inequality of the inequality between this guy and this guy is let me explain that better. No, that's very bad. I made a program to explain this. So let me actually give you this. Let me actually show you the little program I made to explain that. P5J. Also, P5J is kind of a cute little tool for showing graphs and things like that. But yeah, let me show you this real quick. So collision box is collision example, I think. Is it this? Let me check. Yeah. So here you go. So this is a way more graphical representation of the whole spiel. So collisions, at least represented in all of your video games and everything else, is represented by this, right? You have objects that move in this Cartesian plane, and they all have, in order to be drawn into your screen, they need to have values, right? They need to have a x and y value, and often a width and a height. If you see here, the x value is 5. The right value is the value that I have set for the right side of this rectangle, but is based. If you see how it's calculated, it's just the x value plus the width, right? So that's how you got all this, and basically you just run an inequality. Okay, this inequality right here. If this is all true, then there's a collision. Easy as that. I can go and explain all the values like that, but basically you see. It's we can just go through it very fast, but like b1x, so that's box 1x, that is the x value is 9. That's smaller than b2 right side, which is 27. That side. So that means that this side this side is smaller than this side. Okay, that's that. It means that like it's on the same plane around here, right? Same for all the sides, and when you have a true value in all of them, you get a collision, right? So when all these values become true, you have a collision, right? So that is like the first step on it. Like, how do you detect a collision? You just make sure that you compare the dimensions of one square to another square, and if they are all true in this manner, then you got a collision. That was not the best explanation, but yeah. Now, because I'm focused on this other one real quick. So the real deal is now, how do you optimize for it, okay? Because that is one calculation that needs to happen like for two objects, but you never only have two objects. On games or in real life and whatever, you have to calculate millions, billions of collisions, right? And it's actually a very expensive process. Yeah, so for example, we have all of these guys here, right? To run that calculation and be able to like tell the collisions, you need to run the collisions for every item in the system. So this guy needs to check with all of these guys, and then this guy needs to check with everyone else. With this guy, this guy, this guy, this guy, and then this guy needs to check with everyone else, so on and so on, right? So
Exponential process.
yeah, so you need to every new item adds an extra layer of calculations that you have to do that just grows exponentially. Yes, that grows exponentially. So yeah, for every time you add an item, that's another set of calculations that you have to take into account. Okay, now how do you optimize for this? How do you make it a little bit better? In all this stuff, we're trying to reduce the amount of operations that we already did. So if I already checked the collision between this guy and this guy, I don't really need to check it again in my next pass when I check it between this guy and this guy, right? So you're trying to eliminate that. Now, how do you do that? Is, well, you add an index to them, okay? So we'll do it like this. So basically, you add a number to each of them. So let me do this real quick. What? Oh yeah, 0, 1, 2, 3, 4.
Is this relating to gaming?
Is one of the big things is gaming? What?
This is what they would call brownie emotion in I don't know what type of map it's in.
Yeah.
I believe it's in your email. I sent you a model one of my friends sent. It's like an HTML file. You can just run it right now.
Ah, wait.
It might be really cool.
Yeah, no, I will look. Yeah. So yeah, I will do that. Just let me check this out because I want to see what you think about it really. So this is how I optimized it, and I stumbled upon this solution while I was basically drawing this. Is this? So you start from obviously the lowest one, right? And this one needs to check everything else. Okay, this guy checks with everyone else, right? In numerical form, right? Can I? Bruh. Something like that. Yeah, he checks with everyone else, okay? He checks with everyone else, alright? Now, the second one does not need to check with the first one, okay? So if you basically exclude the previous one from your list of checks, you basically, instead of getting an exponential function, you get like an exponential increase on the amount of operations that you have to do. You actually get a logarithmic decrease. So every time that I complete an operation, the amount of operations that I have to do gets lower. Okay, I have checked with all my collision with everyone else. Now I'm in number 1. I'm gonna now, instead of checking everything else, which is the brute force approach, I only check 1 checks with 2, 3, 4, and 5, because I already did the check with 0 and 1. Then when I go into 2, right, I avoid 1 and 0 because that check's already been done. So then I do the check 3, 4, and 5, and then when I go into 3, I only do the check 3, and 5, and then 4 only needs to check with 5, and like that, using it's actually kind of magical the way that it gets together. But if you see, there is not a single line that is not taken into account for, okay? And the way that I did that is by such a simple method, is that every time that you take 1 step, you ignore the guy behind you, right? And that basically improved the performance of my game by like 1,000,000, actually. It was actually incredible. I should actually show you what it looked like before, and I will take a look at the thing that you sent me. But basically, that's what you're running here. And look, this is how the code looks like. So you have a collision with a subject. Okay, the entities is a list of all the possible things that can be in the game. But basically, the target is gonna be the one that you're checking with. So you have a subject and a target. Okay, so if you think about that, in the first pass, the subject is 0. The target would be 1, okay? So because my starting point is, let's say it's 0 here, subject plus 1, so target is equal to subject plus 1, so if the target is 0, the subject is 1. And then I just iterate through all of those, and then the next time when my subject is 1, then my target is 2, and then the next thing is 3, 2, 4, blah, blah, blah. And that's how I avoid checking the one that is before me, and improve like the performance of the game just by me adding basically this line of code here. I improve the performance by a logarithmic amount. That's the best way to say it, by a logarithmic amount, which is very, very good. So yeah, and obviously there's even more and more things to find, but yeah, like as you see, it plays pretty well. It actually used to like hang up and lag a little bit before, but now yeah, it works pretty well. Now you can, and in my other version, I don't have this version right now, but you can also add, I have bullets. Obviously knights don't shoot, but whatever. And each of those bullets is another entity. That's where it becomes crazier and crazier in more like large scale games and things like that. You have projectiles that are moving very fast through the system, right? You have to take account of all of them all the time. And like if you Call of Duty, well, no, Call of Duty doesn't even, Call of Duty's hit skin, but let's say Battlefield. Battlefield is very impressive because Battlefield, all bullets are entities. They all have travel time. That is very impressive because the computer is taking account of all of those entities at the same time, right? And that is not even on a 2D space, that's on a 3D space. So that is something that I found very interesting. I just thought that I would show you guys that because I just find it very cool. Yeah. So you sent me something. Let me check that out real quick. So what is that? So Brownian motion. Let's take a look at this. Is this what that's called?
It's an HTML file. Yeah, this is called Brownian motion. Like they use it for like simulating food. You might have to download it and open it.
I was trying to. The AI was reading your thing right there. Oh, look at that. Let's check out the code. Oh, bruh.
This guy, he's like the best programmer, but he's like a math major or something. So he's like, he knows like what he's doing.
What is he? He's using P5 too? No, he's using Canvas. Oh, wow, he's going raw dog. Wow. Yeah. So let's see what this guy used. So what are you using for? Oh, but no, he's not using. Does he have collision? Oh no, he does. Oh,
Yeah, this is
wow, that's very cool. Yeah. Step 0, generate balls, so that generates the balls. Check collision, so let's see what he did. Check collision AV. So he has a different approach, I think. But let's see. Disregard any checks for the same ball, of course. Yeah, this is my first part. Oh no, actually, I actually don't even have to do this check. I used to do this check. My algorithm skips this check, so my algorithm is a little bit better than his just because of this, but that's okay. Let's see, but let me see what else it does. Create a vector for the different positions. So yeah, you create a new vector to the. I don't know what this function is. That must be something else. He's creating an object.
Collisions, they don't account for mass, right? Or
What?
They don't account for mass. They just account for like if they collide.
Collision is it's only like if they are touching.
So you don't consider like the momentum being conserved. You just say if it hits it, it pushes back.
No. Collision is just the detection. Okay. The reaction can be anything. Like.
So you don't model the actual like.
I do have something for that, but like it's you can activate it, deactivate it. You can do it's a game, right? So like you can have things that just stand in the air, right? Like you disable all. I do have it, for example, like you have the drag and everything there. That's all a function. I can. We want to see it. Well, I don't know if I have it on this program here, but let's see. If you look at the player, for example.
So smart.
Something that I do need to. For that, I do like the mass and everything. I do need to like understand that better because right now the thing that I use because this thing down here is an entity too. This box down here is an entity. So like what happens is that as soon as my guy touches this entity, it changes its position to top of this entity and that's it. And the thing is that it has gravity, so like gravity is what like makes the guy come down. So like it's just a sum that's pushing him downwards on the velocity. Actually, let me show that. Let me see if I can. I made a little show of metadata. This tells. Does it show here? Yeah, you see here, all of the relevant. Some of the relevant information is there, but you see, the x value, the x velocity. You see is. 6 minus 6 plus 6, that's what makes them move in different directions. You jump, your y velocity changes, see? And it's inverted because that's just how these games work. But yeah. It has double jump function. But yeah, the mass is what makes it stop, right? Like because if you have a lot of mass, then it makes it harder to move, right?
Yeah, it has more.
That's something that I haven't implemented yet, but
in this system, right, you assume they have equal masses, so it's a little bit more simple.
Depends on it has a knockback function. So like
I assume these people are of the same size, right?
Yeah.
It kind of makes a little bit more sense.
Well, I
in
won't.
that model, like there's like the big red ball, and that one's like larger, right? So that's why it has.
I gotta look into what your guy did because I want to. I was seeing that he was using vectors on this thing, so that is an interesting one. I want to see how all this works out with each other. Oh, he's using this one. So this is an interesting one because he's using the radius, right? Distance. So the distance. This is actually less efficient because you're using double multiplication instead of like double multiplication is less. Well, not even that. Like you have to do the what is it called? I forget the name of this Greek guy. The Greek guy that does the triangles. Pythagoras, right? You gotta to get distance. You gotta do Pythagoras for every thing. Like for every calculation, you gotta do a Pythagoras theorem to get like the distance from this guy to this guy. And if the distance, basically, I know what he's doing. So the distance is greater than the radius of both of them. It's basically that he's for every guy in that system. He does the distance between all of them, but that is basically the difference of x and y between them, right? And then the Pythagoras theorem to get like the distance in between, right? And then he checks if that distance is smaller than the radius together.
Yes.
Does that make sense?
Yeah.
Okay.
Yeah, I don't know. It might be Pythagoras. You could also make unit vectors because you just
There's no way to not get there's no way to not get distance without Pythagoras. I don't think so.
No, because assuming that these are vectors, and you can like
Well, let's see.
draw unit vectors or whatever. It doesn't matter.
I'll look into it. Okay, yeah, I don't want to bore you guys to that. I'm gonna look into this, but okay. So yeah, well, I guess we're done here. Good stuff though. That was fun. I'm gonna look into that program your friend did. Who did this?
He's one of my friends. He goes to UCF.
I wanna talk to that guy.